None of these other models improved the fit by any significant amount, despite having lots of new free parameters. So after, in the past 2 months, I would say in the aftermath of what we measured in the CMB, I'm very much in a back to the drawing board phase. I don't know. Maybe we've just missed some loophole in the theory. Maybe we need to be much more clever. But at the moment, it's not clear to me what's going on.
Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This episode, I am joined by a friend and colleague, Colin Hill. He is an assistant professor of physics at Columbia University, same place as myself, but as I said, he is in physics, whereas I'm in astronomy. Now, despite that, we're in the same building, we're both in Pupin Hall, and so we often interact. And in fact, the main reason why I really wanted to bring Colin onto the podcast today was because he is one of the most clear-minded physical cosmologists I know. So he studies the origins of the universe, comparing different theories of how the universe began, studying the cosmic microwave background to make sense of it all. And, this is an area where we are seeing a huge number, a record number of kind of controversies in recent years, such as the Hubble tension, the Sigma 8 tension, and the recent DESI result hinting that dark energy could be evolving over time. Now, whenever I hear, personally, any of these very provocative claims being made, be it in the media or be it in a paper, the first person I want to ask is always Colin. And so whenever I see him at a colloquium or a seminar and we're having tea and coffee together or something just before, I'll always sneak over to him and say, "Hey Colin, what do you think about this recent result over here?" So he's really kind of my go-to guy for these lots of questions. And I thought, hey, I should really bring him onto the podcast. And what I wanted to do in today's episode was kind of give you a lay of the land, because there is so much going on in cosmology these days. It is a very active and often an impenetrable field from the outside. It's difficult to know all of these jargon terms. What are people talking about? What measurements are they making? So this is your explainer episode. We're going to go through the basics of physical cosmology, and we're going to get to some of these more controversial results that I mentioned earlier towards the end of this episode. But this should be one of those episodes you bookmark, you come back to. There'll be sections of this that you want to hear a few times, because this is a difficult subject, and Colin is a master of explaining it. So here we go. Please enjoy my conversation with Colin Hill. So I thought we could start today, Colin, by talking about the CMB. Maybe you could explain to us what it is. We're going to need to keep coming back to the CMB, so I think just getting everyone on the same page might be useful. So what is the CMB?
Sure. Okay, good. Yeah, so the simplest statement I can make is that the cosmic microwave background, or CMB, is the remnant heat left over from the Big Bang. So let's just sort of set the stage here in cosmology, starting from the basics. So it's been known since the 1920s that the universe is expanding. So Hubble is credited with the discovery, but there were some other folks involved. But really, in 1929, Hubble posited that the universe was expanding.
From receding galaxies.
Yeah, from the observation that galaxies around us in the universe, outside of our Milky Way, appear to be moving away from us, such that the further away that they are, the faster they appear to be moving away, which is very consistent with the notion that the whole universe itself is expanding. Subsequently, over the past 100 years, that picture has been confirmed. In the 1950s and early 60s, this model was given the name of the Big Bang model by Fred Hoyle, who was actually opposed to the notion that the universe was expanding, but the name stuck.
So it's kind of a joke from him.
Yeah, exactly. Yeah. He was trying to be pejorative, but in fact, the name turned out to be the name that we still use. The reason for that being that if you take the expansion and then hit rewind, it implies that at the very earliest moments of the universe, that everything that we see in our entire observable universe was compressed into a tiny, tiny volume of space, and that there was some, violent, high energy event that happened.
So a singularity, essentially, of some kind.
Yeah, if you extrapolate all the way back to the very, very beginning, it does imply that there is some singularity. We now think that probably the laws of physics become more complicated, particularly the laws of gravity become more complicated as you enter a regime where quantum gravitational effects become important, and that probably resolves this singularity. But yeah, in terms of classical gravity, it implies that everything becomes compressed down to a point. Good. So then this implies that as you compress everything down into smaller and smaller volume, the energy and temperature of the stuff in the universe becomes higher and higher, becomes hotter and hotter. Just like if you compress a gas in a box down to a smaller volume, its temperature goes up, as hopefully we all learned in high school chemistry or physics. And so eventually this implies that everything should be in the form of an ionized hot plasma, and that there was a bunch of hot radiation flying around at that time. This then predicts that this radiation should still be observable today. We just have to account for the fact that the universe has expanded by a lot since that time, so the radiation has cooled down as the universe expands. And in the actually late 1940s, the first prediction of this radiation was made by Elfer and Herman. But somehow no one sort of like jumped on that prediction, was like, let me go test it.
So it could have been detected then?
Could have been detected much earlier than it was. So the discovery of the cosmic microwave background was a serendipitous discovery by Arno Penzias and Bob Wilson, who were working at Bell Labs at the time. And they just constructed this very sensitive, essentially radio antenna, with the goal of communicating with some of the early communication satellites that were in orbit around the Earth in the mid-1960s. And so they went to the antenna, they were pointing it up at the sky, and it was very sensitive, and it had this background noise that they just couldn't get rid of. There was this hiss, basically, in the data. And so they went and they tried to clean out all of the junk in the telescope. Famously, they killed some pigeons that were roosting in the telescope.
Yeah, so it's like bird poop or something.
Yeah,
like
exactly.
Yeah, okay.
Yeah. But
some birds died for the sake of science.
It's true. We appreciate their sacrifice. Yeah, they thought it could be noise from New York City, which isn't so far away from where they were in New Jersey. But nothing would make it go away. So eventually they started to pass word around of their results. Around the same exact time, there was a group in Princeton led by Bob Dickey, who was a very famous physicist of the mid-20th century. And Dickey had gotten interested in cosmology for various reasons. And he had realized, I don't know if he was aware of Alpher and Herman's work, but he became aware that there should be this afterglow, this heat left over from the early universe, if the universe really started with a Big Bang. And he had set his team in Princeton with the task of building a telescope to look for this radiation. And then they got this phone call that came down the road from Bell Labs. And they were told that, well, it had just been discovered.
Oh, no.
And there's this famous quote where Dickey put the phone down and said, well, boys, we've been scooped.
Well, we've all been there. I think in science that's a common happening,
Yeah.
but that's a pretty sensational version of it. Yeah.
Indeed, yeah. So Penzias and Wilson won the Nobel Prize 13 years later for the discovery, completely serendipitous. So what happened was that they published a short paper in the Astrophysical Journal that year that said detection of excess antenna temperature at the frequency of light that they were looking at. And there was another paper on the next page of the journal from the group in Princeton with the theoretical explanation of what the observation was.
Did they know the temperature? Because now we know the temperature is 2.7 Kelvin, but was it known then, or was it just was it a single channel so you couldn't really tell the temperature?
They only had it at a single channel, but if you posit that it's black body, it's a perfect black body radiation, source of radiation, then you can back out the temperature. And their measurement of the temperature was correct within the error bars. I think that they got something like a few Kelvin plus or minus 1 or 2.
Okay.
So it's consistent with the 2.7 number with a much bigger uncertainty than the modern measurements.
And so maybe just to explain, a lot of people often think, and sometimes it's said, but I think it's a mistake, to say the cosmic microwave background, CMB radiation, is light from the Big Bang. But that's not where it's directly coming from. It's really light which emerged some 380,000 years later into the history. So can you explain a little bit?
Sure.
Maybe I'm missing a nuance there as well. So maybe you can give us like where's this light really coming from?
Yeah, good. So let's get into the details a little bit. So as I told you, at the very earliest stages of the universe, the temperatures were so high that all of the matter in the universe was in the form of this ionized plasma. So there were no hydrogen atoms or helium atoms or other atoms. All of the protons and electrons were stripped apart because there was this soup of high energy radiation that they were living in. So the light, the photons, the light was constantly scattering off of the free electrons that were in this plasma. So in physics, we use this term, the mean free path, which is the distance that
before
a
you
photon
bump into something
could travel before it bumps into something. And that distance was very, very short. The photons were always bumping into electrons. The photons had been around for since essentially the beginning. We don't exactly know what happened at the very beginning of the universe. We have this idea called inflation that we can come back to later. We do think that the photons are produced more or less at the end of inflation through a process called reheating. That's very, very unclear at the moment. So the photons are around then, but they're constantly scattering. And so what that means is that you could think of this period in the history of the universe as being a hot, dense fog. So imagine that you're surrounded by this very opaque fog around you, but it's 3,000 Kelvin.
So can I just pause there so when the light is scattered, it's really being absorbed by some ion and then re-emitted. So
it's being Compton scattered off of the electrons in the plasma. So you could think of that as, I suppose, like a very brief absorption and re-emission. But
in your mind, it really is the same photon in that sense, because you could think it's a distinct photon that's been.
Yeah, I sort of think of the whole bath of photons as existing more or less since reheating. But the important fact about this is that because of this scattering process, it means that the universe is opaque during that period of time.
Right.
So then let's go continue going forward. So after about 380,000 years go by, the universe cools down enough that now the electrons can combine with protons to form neutral hydrogen atoms. And this is the key moment because light does not efficiently scatter off of neutral atoms. And so the photons then can free stream through the universe, essentially unperturbed. And that instant is what we call recombination or last scattering. The word recombination is sort of funny because it was the first combination of the electrons and protons, but for astronomical jargon reasons, we call it recombination. So that's the moment of last scattering. The photons then travel through the universe. And that moment is what we see when we look at the cosmic wave background. So those photons are undergoing their final scattering off of the free electrons that are present. The photons then travel. Recombination happens very quickly, so the universe transitions from being this ionized plasma to being this neutral gas of mostly hydrogen atoms, and the light then free streams to us.
And this, obviously the universe is extremely homogeneous, which is one of the things we know from the CMB, but this process presumably didn't happen in an instant. There would have been regions where it cooled down slightly sooner than other regions, so the light would have been emitted at not all at exactly 380,000 years. Some of it would be a little bit ahead, some behind.
Yeah, that is correct. You can think of recombination as being a slightly inhomogeneous process. There are some general relativity subtleties in how we talk about these things, but in a particular gauge of GR, that is a correct physical picture to think about what's happening.
Yeah, it kind of reminds me of the sun, because I think it's true, people often say this about the sun, that a photon produced in the core of the sun takes like 8 million years or something to make its way to the surface.
Yeah, because it's constantly scattering.
Yeah, right? So it takes even though it's not, obviously the actual physical distance will only take it probably, certainly less than a minute to make that journey.
Right.
It takes it, 8 million years, and then when it gets to the surface, that's kind of the analogy here of the moment of recombination, when it's now allowed to free stream through space.
Yeah.
Okay. So we've heard a little bit where it comes from, the first detection. What were the early experiments that were not just detecting its existence, but actually learning something about the CMB?
Yeah, good. Okay, so now after it was discovered in 1965, it became clear that there were two lines of extremely important inquiry that needed to be undertook. So the first one is that based on the Big Bang prediction, this radiation should have effectively a perfect black body spectrum. So Mr. Planck wrote down in 1900 the famous form of the black body radiation distribution. And the idea here is that because the universe was so hot and dense early on in this Big Bang picture, that the radiation should become extremely thermal through constantly scattering off of all the other particles. So that was a robust prediction. But to show that it follows a thermal Planck blackbody distribution, you have to go out and measure this radiation at many different frequencies of light and show that it follows the blackbody curve.
Were there alternatives? Were people saying, no, it might be something else?
Well, yeah. So there are other possibilities. For example, if the radiation wasn't perfectly thermalized, then you could expect that there should be spectral distortions away from this blackbody function. And maybe we can turn to this later.
Yeah.
But in fact, the standard model of cosmology that we now have does predict that there should be tiny distortions, but they're 1 part in 10 to the 6.
Right.
So very small. Whereas these alternative scenarios for the formation of structure, for example, could predict that there was order 1 deviations from the blackbody distribution. So that was the first important thing that needed to be done, was to check that it followed a blackbody distribution. And there were a variety of experiments in the 70s and 80s, culminating in the COBE-FIRAS. So COBE was the Cosmic Background Explorer was a NASA mission launched in 1989. It had several instruments, but one of the instruments on board was called FIRAS, Far Infrared Absolute Spectrophotometer, which essentially went out to measure this distribution as a function of frequency and found that it followed this perfect black body distribution. When they unveiled the measurement at the meeting of the American Astronomical Society in, I think, 1991 or 92, they got a standing ovation in the crowd.
I've only heard of that happening one at a time. That's pretty amazing.
Yeah. I mean, everyone just immediately knew, like, wow, this is like
game changing.
Boom. Yeah. There it is.
What point? You must have been like
I was alive.
Yeah. Very young at that point.
But I was a small child.
Yeah.
I wasn't yet aware of it, what was going on. I should say also that the history is a little it's complicated because there was actually a sounding rocket experiment that was done by a group from the University of British Columbia. I think the PI's name was Thrush, if I remember correctly. And they launched this sounding rocket to make measurements from the upper atmosphere of the spectrum very shortly before the COBE-FIRAS results came out. And they actually found the black body curve with somewhat larger error bars, but they really had found this around the same time. So it's worth giving credit to this group.
Was there a Nobel Prize for that, I think?
So the PI of the FIRAS instrument, John Mather, he won the Nobel Prize shared with George Smoot, who we'll come to in a second. But the other group did not share in the Nobel Prize. Yeah.
Okay.
Okay, so that was the first major thing that had to happen, was to show that it followed a black body distribution. And again, this COBE-FIRAS measurement just nailed the door. It said, okay, the universe started with a big bang. Okay, so the second important thing to try to understand was this question of the inhomogeneities in the radiation. So now we're talking about the spatial properties of this radiation. So we should expect that it's a little hotter in one direction and a little colder in one other direction if you compare them. And the reason for that is that we know if we look out in the universe today around us that it's very inhomogeneous. You look in one direction, you see one galaxy, and then there's a huge void of empty space until you find the next galaxy. So very significant deviations in the density from place to place in the universe. How did it get that way? Well, the basic picture that we have is that gravity acts to pull stuff together over billions and billions of years. And it makes the universe more inhomogeneous. If I have a little overdensity in one place, that will attract more and more matter as time goes on, and it will empty out the surroundings around it. So the qualitative picture of how this should happen is pretty clear. But then there's a quantitative theory that needs to be built up to say, how do we go from the initial inhomogeneities at the very beginning of the universe to the inhomogeneities that we see today in the distribution?
So if you had a purely homogeneous CMB or initial starting conditions, it'd just simply be impossible to have the structure.
That's right. Today. Yeah. So if it was perfectly homogeneous at the beginning, it would stay that way because all the forces would exactly cancel on every other element. So this qualitative picture was clear, but what wasn't known was how large the initial inhomogeneities were. And the way to figure that out was to go measure them in the cosmic microwave background, which is the earliest light that we can see because of this opaqueness that I talked about earlier, right? It's before that moment, the universe is opaque to us. It's this hot, dense fog. So the earliest time we can see with light is the moment of last scattering with the cosmic microwave background. And there was a huge range of predictions from theorists at the time. No one knew exactly how large the inhomogeneities or fluctuations in the CMB should be. So that started a 30-year quest to go out and detect the inhomogeneities. And it was a long and difficult path where there was just upper limits for a long time as they kept looking and not finding them. The theorists would revise the predictions a little bit. The realization that dark matter exists turned out to be a key role in determining what these inhomogeneities should be.
So COBE didn't detect any of these.
Well, so that's where I'm coming actually next.
Okay.
So there was a bunch of upper limits, and then spectacularly in the early 1990s, there was a different instrument on board the COBE satellite. This one was called DMR, the Differential Microwave Radiometer. Apologies if I got that wrong, but I think that's what it was, DMR. And so DMR was meant to look for the differences, hence the name differential, the differences in the temperature from place to place on the sky. And it was, compared to the instruments we have today, it wasn't very sensitive. But at the time, it was revolutionary, and it was able to make the first detection of these anisotropies, or differences in the temperature from place to place on the sky. And that discovery was awarded the other half of the Nobel Prize in 2006. So Mather won for the discovery of the black body spectrum, and then George Smoot, who was the PI of the DMR instrument, he won for the discovery of the anisotropies.
So what is the order of magnitude of the temperature differences?
Yeah, so what Kobe found was that it turns out to be about 1 part in 10 to the 5. So the average temperature of the CMB on the sky, as you mentioned earlier, is about 2.7 Kelvin. So 2.7 degrees above absolute zero. It's very cold, hence why we didn't notice it till 1965. And the differences in the temperature from place to place on the sky are about 1 part in 100,000.
Wow.
So about tens of microkelvin.
So if it was, let's say, 1 part in a billion or 1 part in a trillion, would you even have structure? Have people calculated like you need at least a certain amount of?
So the challenge that we would run into is that there wouldn't be enough time to go from the moment of last scattering to the modern universe to grow the galaxies that we see in the universe today if the initial perturbations were that small.
Yeah.
In fact, people were surprised that they turned out to be as small as they were. And that was because dark matter plays a key role in the formation of structure. And in the 60s and 70s, people weren't really aware of the important role that dark matter plays.
Because that kind of amplifies the structure growth. Yeah. So if you didn't have that, there wouldn't be enough time.
That's right.
Which is kind of evidence for dark.
In my opinion, it's the strongest evidence for dark matter, actually.
Yeah.
The formation of structure in the universe would just look nothing like what we actually see in the universe we live in if there was no dark matter.
Interesting.
Yeah.
Okay. So there's many different aspects that we can measure from the CMB, many different properties. You're an observational cosmologist, so these are your tools of the trade. And I want to kind of go through a few of these different things that we often use and hear about. So the first one is the most obvious one is the CMB temperature power spectrum. That's I think if you've seen any plot from the CMB, besides the actual, globe itself, you've seen this kind of plot of the multiple wiggles and poles. It kind of looks like a snake or a sine wave going up and down. What is that actually measuring, and why is that such a powerful measurement? What is it teaching us?
Okay, so we have a lot to unpack. I'd say the technical answer to these questions requires like a course in cosmology.
Try and give us the it's okay to skip some details, just the abridged version.
Well, let's get through the qualitative aspects. Okay, so we talked about the average temperature of the CMB being 2.7 Kelvin, and then we measure these small differences in the temperature from place to place that are on the order of 1 part in 100,000. So then we have to ask, what type of question can we ask about the universe that we could answer with this data? So the first important thing to note is that our theories of cosmology are stochastic in nature or statistical. Mm-hmm. So our theory doesn't predict, for example, that the Milky Way should have formed where it currently is. We don't actually know a priori what the initial conditions of the universe were. And so we can't predict there should be a galaxy there or a hotspot there. Okay, so this then tells us what we need to measure are statistical properties, or what we call, in more technical parlance, correlation functions of the fields in our universe. So the distribution of matter, for example, or the distribution of galaxies, or the distribution of hot and cold spots in the CMB. So if you look at one of these maps, for example, from Planck or WMAP, or now the ground-based experiments like ACT or SBT, what you see are these patterns of hot and cold spots. And then what we want to do is to measure these statistical properties, which are the things that we can then compare robustly to our data. So our data can predict, for example, our theory can predict if I see a hotspot in this direction, what's the probability that there's another hotspot separated by angle theta on the sky? Mm-hmm. Our theory can predict this, and it's something we can measure from the data.
So why should there be any correlation? If you've got one hotspot, why would you expect at all there to be another hotspot a certain distance away?
So this is related to the properties of the initial perturbations from inflation. Mm-hmm.
So the scale of quantum perturbations, essentially.
Yeah. So if we go back even further in the history of the universe, there had to be some process that produced the initial fluctuations in the distribution of energy. And our current best hypothesis for what that process was is something called inflation, which posits that the universe expanded exponentially during the first fraction of a second of its existence. At that time, the universe was so small that the relevant laws of physics that are operating are quantum mechanical. And quantum mechanics tells you that, the Heisenberg uncertainty principle tells you that you can't perfectly localize something like, let's say, some amount of energy. There's always going to be some intrinsic quantum fluctuation or uncertainty when you try to do that. So through a detailed set of calculations that was first done in the early 1980s at a famous workshop in Cambridge, you can calculate what we call the power spectrum, or let's just say how strongly correlated as a function of position in the sky these fluctuations should be from inflation. And ultimately it's coming from quantum mechanics. So there are these quantum mechanical perturbations.
So the entire prediction of the CMB power spectrum, the temperature power spectrum, is a prediction of inflation.
It is, yeah. And there's a number of ways in which it manifests. There's actually something that's even cooler, which is a little bit hard to describe because it's kind of technical, but I'll try because I find it to be so amazing. So one of the cool things about inflation is that what happens is you generate these perturbations through these quantum mechanical fluctuations during that epoch. The fluctuations actually get stretched out so quickly that they leave what we call the causal horizon. So they actually become causally disconnected from each other as they leave the horizon. The horizon is imposed because the speed of light is a finite number. So they leave the horizon. They actually then get frozen outside of the horizon, and after inflation ends, they then re-enter the horizon as sort of the horizon is then expanding and it catches up to the frozen perturbations that are outside the horizon. And by virtue of the way that they get frozen outside the horizon, what happens is that all of the perturbations of a given wavelength re-enter the horizon, what we say, in phase. So it's as if you had a bunch of waves and you're setting them all off at the exact same time. And this is a key prediction of inflation that other theories for the formation of structure do not make. So for example, if you have a theory that forms the perturbations through some dynamical process that's sub-horizon, like setting off explosions inside the universe, which used to be a theory in the 70s and 80s, that does not predict that the fluctuations would all re-enter the horizon in phase. And then because they re-enter in phase, they interfere constructively. And that constructive interference is what really is responsible for the beautiful structure of the peaks in the CMB power spectrum.
So this is we had Will Kinney on in the last podcast I interviewed, and he was talking about his book on inflation, a popular science book.
It's a great book, yeah.
Yeah, and he explained the super horizon scales are in the CMB.
That's precisely what I'm referring to.
Are really it's very difficult to explain those without inflation.
That's right.
So
that's right.
Do cosmologists sort of accept inflation as canonical at this point, or is there still people who hold out to other ideas?
I would say that it remains the leading paradigm. There's certainly other ideas that are still discussed and taken seriously. Maybe the most popular alternative idea is this idea of a cyclic universe, which goes through phases of expansion and then contraction and then expansion. And that also does predict in a different way the existence of these superhorizon correlations. People debate about other aspects of what this model predicts compared to inflation. But yeah, inflation remains the leading hypothesis. So then let me close the loop on the CMB temperature power spectrum. So good. So now we understand why there should be these correlations between the spots in the CMB. So one way of quantifying this is what I said earlier, where you just say, if I have a hotspot here, what's the probability of having a hotspot located by a distance, separated by a distance theta on the sky? We would call that the 2-point correlation function of the hot and cold spots. And then if you could take a Fourier transform of that, that's the angular power spectrum. So
to go from spatial scales to frequencies.
Yeah, they're angular frequencies on the sky.
Yeah.
So we like to think in Fourier space for various reasons in cosmology. So the way to think about it is just what the graph is showing you with these wiggles is if I look in the map at a particular angular scale, say the scale of 1 degree, which is roughly twice the width of the moon on the sky, what is the typical contrast of the hot and cold spots in the map on that angular scale? So if the map was perfectly homogeneous on that angular scale, the power spectrum would be 0 because there would be no contrast. If the map had huge fluctuations, like plus or minus 1 Kelvin, well, then the power spectrum will be enormous at that angular scale. And so we look at that as a function of angular scale, and it tells us how large is the typical contrast or fluctuation in the map as a function of angular scale. And that's the quantity that our theory can robustly predict. And then we compare the theory to the data and infer the basic parameters of the universe.
Yeah, I'm wondering if there's a musical analogy with the Fourier. I mean, obviously with Fourier transforms, we often think about a musical analogy, that you've got these, if you listen to music being played, someone finger picking on a guitar or something, you hear these individual notes in Fourier space, but our ears really just hearing continuous noise. There's no like gaps in the music unless they pause for a moment. So there's just continuous sound. But when you go to the Fourier domain, you see in frequency space there are huge gaps, and there's just these very sharp peaks of the notes individually that the guitarist is plucking. And so in a way, this is really saying that the universe has the same kind of overtones. There's these specific kind of frequencies where you really are much more likely to see correlation, almost want to say causation, but it's kind of weird to say causation because they're so far separated. They shouldn't really, by the speed of light, be interacting with each other, and yet there are still these
certainly for the largest angular scales in the CMB.
Yes, the largest scales. Yeah, but the smaller scales
that's causal processes that produce those. Yeah. The musical analogy is a nice one. I think people have sonified the CMB power spectrum. If you look online, you can find some of these things.
It'll be fun to listen to. I've seen sonifications of exoplanet resonance systems the same way. TRAPPIST-1's a very famous one. If you want to look that up, it's really fun. There's a TRAPPIST-1 like concerto where they've they've managed to find all sorts of ways to add different like drum beats and all kinds of stuff. It's really fun to listen to. So
very cool.
We have the power spectrum, but it's not the only power spectrum. There's all sorts of power spectra you hear about with the CMB. There's also the polarization spectra.
Yes.
So maybe obviously polarization, we're kind of familiar with polarized glasses, how you can block out sort of the rotation of the light itself. We all know that you get better contrast when you wear polarized glasses when you're driving or something. We can basically do the same effect when we look at the sky. Why would you expect light to be polarized coming off the CMB? Why is this a useful thing to do?
Yeah, good. So let's just remind what polarization is. Just the direction of the electric field that's oscillating as part of a traveling light wave. So the reason the CMB is polarized is actually the same as the reason that the light that you see scattering off the surface of a lake or a puddle is polarized. And it's because the process of Thomson scattering, which is what's happening at the last moment of last scattering, the process of Thomson scattering is intrinsically polarization sensitive.
It's not Compton. You said earlier it's Compton.
I would use those two words interchangeably, but Thomson, Compton, the low energy limit of photon electron scattering.
Yeah. So this process of a scattering reflection almost that always manifests in some kind of polarization.
In general, yes. There is one particular subtlety here that's very important in the case of the CMB. So let's imagine we're an electron at the moment of last scattering. So the electron is seeing the local radiation field around it. If that local radiation field was completely isotropic, then the outgoing radiation would be unpolarized. So the salient feature of Thomson scattering here that's important is that the strength of the scattering cross-section, how sensitive it is to the incoming light, depends on the angle that the light makes with respect to the outgoing light wave. It has a quadrupolar dependence, which looks like it, maximal here, and then 90 degrees, rotate by 90 degrees, it'd be minimal, and then by 90 degrees, it'd be maximal again, et cetera. So as a result of that, what's important is that the incoming radiation has a quadrupolar anisotropy in it because of the intrinsic temperature differences in the radiation field around the electron. And so the incoming radiation has this quadrupolar dependence. And as a result of that, the outgoing light after the Thomson scattering happens acquires a linear polarization. This is the origin of the polarization.
And so that polarization encodes something about the environment.
Yeah, it tells you about the local quadrupole that the electron sees. Or in less technical language, it just tells you how inhomogeneous is the local radiation field around the electron.
Yeah.
So it gives you access to a slightly different set of information than what we see when we look at just the temperature of the radiation, because it lets us see, okay, like what was the local field around each electron at that time.
So if the universe was purely homogeneous, there'd be zero polarization then, by that logic.
That's right. Yeah, that's right.
And if you had a completely bifurcated, odd even, almost like hot cold setup, that would maximize the polarization. How would you think about maximization?
Yeah, the larger that the local quadrupolar anisotropy is, the larger the polarization will become.
Okay.
Yeah. So if the local quadrupole that the electron sees was of the same order as the what we call the monopole temperature perturbation, then the polarization could become as large as the intrinsic temperature.
Got it. Yeah, I just think I sometimes think it's always good to think about the limits of a function, right? I always like to think about like what happens when you go to the zero case and the maximal case, and then whatever you see, you can think of as some boundary between those 2 points.
Yeah, if you want some sort of typical order of magnitude, as a result of this process, the CMB ends up being polarized at about the 10% level. So if you look at the differences in temperature from place to place, that gives you a typical inhomogeneity or fluctuation of order tens of microkelvin, and then the polarization differences from place to place in the sky are a factor 10 below that. So about 1 microkelvin, 1 part in 10 to the 6.
So we have the CMB polarization spectrum. And one thing we often hear about with this spectrum is the E and the B modes, which I think is E is electric, B magnetic, or at least that's sort of the historical.
That was the inspiration for the names.
But it doesn't really, when you actually see them portrayed, seems to have nothing to do with that. So yeah, explain to us what are these E and B modes, and the connection, of course, to like BICEP 2, the gravitational wave searches people have been doing for these.
Yeah, good. So as we've discussed, the CMB is polarized. So that means that, and then there's going to be fluctuations in the polarization from place to place on the sky, just like there's fluctuations in the temperature of the radiation from place to place on the sky. Just random. Yeah. But there's correlations just like there is in the temperature. And those correlations are important because that's the substance of the data that we can compare to theory. So the name of these E and B modes just comes from the fact that polarization is what we call a headless vector field. So it's like a vector. It points in a direction, but it's symmetric in the sense that there's no, it's not pointing like, if it's pointing up, it could equally well be pointing down. It just defines like an orientation, if you will.
Okay. So I guess what's different there from temperature, which is just a scalar.
That's right.
It's just a number of what the temperature is at each point of the CMB. If you made a map of the polarization, there's really like a little arrow. There's a direction at each point.
That's right. You should think of it like that. And you need 2 numbers to specify this direction. Conventionally, we use what are called E and B modes. That's the slightly technical definition of this is that the B mode is the divergence-free piece of this vector field, and the E mode is the curl-free piece of this vector field. You can think of it basically like the E modes look like the arrows that are all pointing either towards a point or exactly tangentially around a point, and the B modes look like these swirly patterns around a point. And the names of E and B are inspired by the connection to electric and magnetic fields in electromagnetism, because they have the same mathematical properties, but fundamentally they're not coming directly from electric and magnetic aspects. That's just a mathematical analogy that we make.
So it's a bit of a misnomer to call them electric and magnetic.
Yeah. So we just stick to E and B.
Okay. They almost sound like, if you've got the radial, so the E is the radial and the tangential directions, and then you describe the B as sort of the curly,
swirly,
the wiggly ones.
Yeah.
So that almost sounds like it's higher order, and therefore I would think it would be more difficult to detect. Is that true or not?
So that turns out to be true, although the reasons are a little complicated and definitely not worth going into here. But what turns out to be really important about this decomposition is that if we think back to the original perturbations from inflation, so these quantum mechanical fluctuations that gave rise to all the structure in the universe, those are responsible for the fact that there's a little more matter in one location, a little less matter in another location. So ultimately, they're responsible for our own existence. These quantum mechanical perturbations predict not only that there should be density perturbations, or what we've called scalar perturbations, but also that if inflation was the relevant process that created the perturbations, that there should be gravitational wave perturbations that are also produced. And what is very interesting is that the scalar perturbations or density perturbations, those produce the temperature differences in the CMB. They also produce the E-mode polarization differences in the CMB, but they do not produce B-mode fluctuations or differences in the CMB. So only the gravitational wave perturbations from inflation, if they existed, would produce the B-mode perturbations. So this is why it's so exciting to us as cosmologists, is that if we made a detection of these B-mode polarization fluctuations on the sky, these swirly patterns, that we could then say we've measured gravitational wave perturbations produced during inflation. It's a very clean probe. There's very little theoretical messiness involved in the theory underlying that observation.
Well, let me just push back
the
a little
observations
bit.
themselves
Yeah.
are a whole different story,
Right,
where we can come
I think
to
there
next.
are other things which can create these swirly patterns, right? Such as dust in the
Good. So the astrophysics is another story. The cosmology, the early universe cosmology is theoretically very simple and clean. And if we could make a robust detection of these B modes, we would say this is pretty much the most smoking gun evidence you could hope for to say we know how the universe started. Which, I mean, as human beings, that's a pretty incredible thing for us to be able to say.
So if you knew the photon was emitted from the CMB, and you measured this ensemble of photons to have a B mode pattern, that would be slam dunk of primordial gravitational waves, which is a signature in turn of inflation. But the problem is, when you see this pattern, you're not really sure whether what you're seeing is truly the CMB or something much closer to home, a foreground source.
That's right. So the big challenge in this particular aspect of CMB measurements is that, as you say, at the wavelengths of light that we're observing on the sky, the cosmic microwave background is not the only source of emission. So we have to contend with the fact that we're looking out through our own galaxy, the Milky Way, which is filled with these beautiful dust patterns that we have seen and studied. So the dust is emitting at these wavelengths of light because it's being heated by starlight from the stars in the Milky Way. That then warms it up a little bit, and so it glows thermally. It's just thermal emission from the dust, and it's pretty cold. It's at a temperature around 20 Kelvin, so it's a little hotter than the CMB, but by our standards, very cold. And so it emits thermal radiation, nearly thermal radiation, at these same wavelengths of light, and it can produce B-mode patterns. It has no theorem that prevents it from emitting B-mode patterns, and so we have to go out and measure not only the CMB, but also these astrophysical sources like dust. There's another one also from what we call synchrotron radiation, which is radiation from electrons spiraling around in the galactic magnetic field. You might say, well, okay, how could you ever solve this problem? How could you ever make a measurement to know which one is which? And the key aspect is that the colors of these different signals are different. So what we call the spectral energy distribution in astronomy parlance is different. So the CMB...
Because one's hotter, one's 20 Kelvin, one's 3 Kelvin.
That's a clear, clear argument for why they should be different.
Yeah.
As you talked about earlier, the CMB follows this perfect black body spectrum, been confirmed amazingly well by Kobe Firas. So we know what that should look like as a function of the wavelength of light, whereas the dust generically will not look exactly like that, and the synchrotron radiation also definitely does not look like that. It actually has the opposite frequency dependence, where it gets fainter at higher frequencies.
Okay.
So if we can make measurements of the sky at multiple different wavelengths of light, and use sophisticated data analysis techniques, some of which are things that I've worked on for many years, we can then synthesize our observations in such a way to clean out all those contaminants and just leave this, holy grail signal, if it's still there, if it is actually there in the cosmic microwave.
Let me just track back to something you said quickly there. You said about the slopes being opposite. So is that because the frequency range in which you're doing these measurements is on the tail end, the rally tail essentially, as we'd say, of the CMB, but it's on the upward slope part of the Planck function of the 20 Kelvin dust?
Well, so we're in the Rayleigh-Jeans tail of both the CMB and the dust. Well, actually, with the CMB, we try to make measurements that span the entire range from the Rayleigh-Jeans tail all the way to the Wien tail. The bulk of our sensitivity is in the region where it's more Rayleigh-Jeans-like. So it's the CMB is increasing as a function of frequency. The dust is definitely also increasing as a function of frequency, even more steeply than the CMB. And then the synchrotron radiation has the opposite dependence, where it is decreasing as a function of frequency.
Okay.
Yeah. Sort of like a power law, basically.
So this, just to clarify, this hasn't been detected yet. There was obviously the famous claim, Bicep 2, and I interviewed Brian Keating about that, and he wrote a book about that. So people should check out that podcast. But that was a few years ago. So even today, there is still no convincing detection of this.
That's right. So we have not yet detected these primordial gravitational waves from inflation, or what we call these B modes in the CMB. We've only detected the foreground B modes from the dust. There's also a contribution that comes from gravitational lensing of the CMB. It can produce some B modes. We know how to calculate that, so it's not a big worry. We've seen those, but we have not seen the primordial B modes that would be produced by the gravitational waves. So there's a number that we call R, the tensor to scalar ratio. And the search for these gravitational waves is just a search for this one number. The basic story is that. So the current upper limit on this number comes actually from successors of Bicep 2. The latest one is called Bicep Keck. They have a new project called Bicep 3. They're continuing to observe at the South Pole. The upper limit from that project is about 0.04, 0.036, I think, at 95% confidence. So that tells you that the gravitational wave perturbations from inflation, if they do exist, are at least a factor of 25 smaller in amplitude than the scalar density perturbations that we have studied and detected. So the upper limit keeps getting smaller and smaller. And what this corresponds to is then constraints on the physics of inflation itself. What type of fundamental fields could have operated, and particularly what the energy scale of inflation was. So we're continuing to make these measurements. The next big project that's happening is called the Simons Observatory, which I'm very heavily involved in. This is a project in Chile where we've had other ground-based CMB experiments. The Atacama Desert of northern Chile and the South Pole are sort of the two best sites on the Earth for making these measurements because they're so high and dry. The water vapor in the atmosphere is the main contaminant that we have to deal with. So we try to go to these remote, high and dry places. And we're trying to push the sensitivity to these gravitational waves down by at least another factor of 10, ideally more than that over the next decade or so.
But there's no guarantee, even if inflation is correct, even if it did generate gravitational waves, there's no lower limit as to how small they could be.
Formally, there is a lower limit, but it is so many orders of magnitude below what's feasibly detectable that we don't even speak of it. Yeah. So there's no guarantee that even if inflation happened, that we could detect these B-mode patterns. It's possible that they're just so faint that they're far below the sensitivity of any experiment that we could ever build. But
do you have a hunch on that? What do you think?
I like to be optimistic when it comes to these things. So I'll just say that there are some really important theoretical benchmarks in the world of inflationary model building that predict values of this tensor to scalar ratio, these gravitational waves, that are detectable in the next 10 or 15 years. And so I think we definitely should work as hard as we can to hit those benchmarks. If we get past those and we don't see anything, then I think it becomes a bit of a Wild West where we don't know from a theory standpoint if it's as well motivated to continue searching. I think as humans, we're always compelled to remain curious and keep looking. But like many things in astronomy and cosmology, we have to kind of go out and look and hope that nature is kind to us. Sometimes it throws unexpected curveballs in our direction.
Yeah, it kind of reminds me a little bit of the search for dark matter particles.
It's very similar in that.
There's no guarantee that dark matter isn't just a particle that doesn't interact with anything except via gravity.
That's right.
And if that's true, then all these experiments we're doing are they're not a waste of time because they're putting limits, but they're never, no matter how much we improve it, there's no limit. We can improve it, become a galactic spanning civilization, and we'll still never detect the dark matter particle.
That's right.
And a lot of people get frustrated with these ideas when that's true. So they might say, if you can't falsify the idea, you can't really falsify inflation then, can you? If you can never no absence of evidence of the B modes would ever rule out inflation.
That is true. I think what is important, though, is that we could rule out entire classes of inflationary theories. So you can sort of group models of inflation into two different categories, one of which we call large field inflation, one of which we call small field inflation. Mm-hmm. Roughly speaking, the models that live in the large field inflation category are the ones that predict observable gravitational waves that we could see in our lifetime. If we rule out all of those, then from a fundamental physics standpoint, we've just made a huge leap forward in terms of our progress and understanding what happened at the beginning of the universe. It's kind of like turning on a particle collider. In fact, it's exactly like turning on a particle collider at some higher energy and looking for the particles that could have been produced and then not seeing those particles. Of course, it's disappointing, but when you go back to your theoretical model building exercise, you can say, well, now I've ruled out a huge swath of the space and I have a much better idea of what the true theory needs to look like. Unfortunately, physics doesn't have to comport with our human timescales that we live on. The 20th century was a period of remarkably rapid progress, even on human timescales, and so we maybe became accustomed to that. But I sort of like to think on more like millennium-long timescales, and if you think about the progress that we've made since 1,000 years ago, it's just unimaginable, and I think that 1,000 years from now, that'll be the case. Whether it happens like in our own century or not is kind of a random chance.
This isn't a Hollywood movie. There's no reason why we have to have the Hollywood ending in each of our lifetimes. It could just be a multi-generational thing.
Yeah, but it's so crucial that we keep looking, right? If we don't look, we have zero chance of finding anything.
Absolutely.
Yeah, was it the sports quote? You miss 100% of the shots you don't take.
Right. Yeah. Same with looking for alien life. Yeah. In exoplanets.
Yeah.
So before we leave polarization, there's also birefringence. I'm actually familiar with birefringence mostly because I did geology as a first year student at Cambridge. We do natural sciences, and we had to measure the birefringence of tons and tons of minerals. I remember it being like the most painful thing. I hated it so much. But maybe you could, obviously that's not the kind of birefringence, what's analogous in cosmology you're trying to measure. Explain to us what this is from the polarization, and has there been any detections of birefringence?
So this is a topic that's recently had some activity after many years of kind of being dormant or a little bit on the fringes. The idea of birefringence in the cosmic microwave background is pretty simple. The basic idea here is that there is some polarization that gets induced at the surface of last scattering, which we talked about earlier. In the standard model, that polarization does not rotate as the photon travels to us through the universe. In some what we call beyond standard model theories, so theories with extra new physics in them, the plane of polarization itself can be rotated slightly. So if you had an initial E mode pattern with no swirls at the surface of last scattering, that can be rotated a little bit and produce some B modes, some of these swirly patterns as a result of that rotation. And that's what we call cosmic birefringence. So in the standard model of cosmology, this should not exist. So it's expected to be zero. Intriguingly, there have been some moderate hints, not a 5 sigma detection, but some moderate hints perhaps in the data.
Well, how can you detect it? Because if you don't know what the true original rotation was, so how do you know that the rotation you're seeing is different to where it started?
Yeah, so the crucial statistical fact of this process is that it leads to a residual correlation between these new B modes that get generated in the CMB and the E modes. So in the standard model, the correlation of the E field with the B field is exactly zero. But if you have birefringence like this, you produce a small correlation between the E and the B field.
But we haven't detected the B field. So how can you measure birefringence if you haven't got a B field yet?
This would produce detectable B modes, but they have different properties than the primordial gravitational wave B modes in some sense, so their power spectrum looks.
I guess just clarify my question: if someone has claimed the detection of birefringence, does that necessarily mean they have also detected B modes?
Yeah, but not the primordial gravitational wave B modes.
Oh, okay.
It's sort of like the detection of gravitational lensing induced B modes. So as I talked about earlier, the process of lensing of the CMB, just the bending of the paths of the photons.
Oh,
by
so this
lensing,
is an extra way of creating B modes. So
right,
before we had this picture that B modes can only be created by, obviously there's dust, but primordially they can only be detected by gravitational waves. But now there's an additional mechanism, which is the journey through 13.8 billion years of light travel time that will cause an additional B-mode effect, but only in some exotic theories of cosmology.
Yeah, there is one standard process, which is gravitational lensing of the CMB. So as the CMB photons travel to us, their paths get bent very slightly by the gravity of all the structures in the universe, like clusters of galaxies. And that process also slightly deforms the E field into a little bit of a B field. And we know how to calculate that. There's some very nice calculations you can do in general relativity, and we can compute what this looks like. Okay. So that produces some B modes, and that's already accounted for in everything that we do.
And has been detected.
Yeah, and it's been detected. Mm-hmm. Yeah, exactly. But this birefringence would be yet another way to produce some B modes through a process that happens as the photons are traveling.
So would it look like excess gravitational lensing, or would it look completely different?
It could look slightly like that, but the key thing that the birefringence produces is a correlation between E and B, which the gravitational lensing does not. Okay. Yeah. So that lets you distinguish between them.
So what's the observational status of that signal?
So there have been some hints from, I would say, reanalyses of the Planck satellite data, which was the last satellite mission we had that observed the CMB, launched by the European Space Agency, also with NASA contributions. There have been sort of 3-ish sigma, maybe 4 if you're optimistic, sigma hints of some cosmic birefringence in that data. It's a very challenging problem, though, because if we return back to this question of foregrounds and dust, the dust can also produce some EB correlation that looks a little bit like this. I've looked into this and wrote some papers about this a couple of years ago with people.
Okay.
So the challenge right now is trying to distinguish between what could be cosmic and what could be foreground related. The other challenge on this front is related to properties of the instruments themselves. So in order to know what's E and what's B on the sky, you have to know how your instrument, really your polarimeter, is oriented with respect to the sky emission. So there's an overall angle that you have to know. We just call this the overall calibration angle of your telescope. And you have to calibrate that really, really precisely to make these kinds of measurements. Previous to the current excitement, I would say cosmic birefringence wasn't motivating us to try to do that calibration super precisely, or at least not more precisely than we would have needed for our searches for primordial gravitational waves. But now, because of this, we're trying to think of more clever ways to calibrate even more precisely in order to potentially confirm or refute this hint of birefringence.
And what kind of models are we talking about they would imply?
Yeah, so what type of new physics could do this? So the one that's maybe most exciting is a model in which we introduce what's called an axion field. Axions are an extension of the standard model of particle physics that were introduced back in the 1970s to solve.
I'm thinking of dark matter when I hear axions.
Yeah, now they're a popular dark matter candidate. Yeah, they're really like a generic type of particle that you could add to the standard model and is technically natural, well motivated, and it, for some types of axions, can solve other problems in the standard model of particle physics. For our purposes here, though, let's just say it's a particle we're allowed to add to the theory, and then a natural expectation that you would have from a particle physics standpoint is that this new axion particle can couple to the photon. So there can be an interaction between the axion field and the photon, the light in the electromagnetic sector. And that coupling, for certain types of axions, can rotate the polarization of the photon as the photon is traveling because of the evolution of the axion field and the interaction between them.
Would that come into tension with the actual particle axion searches, which keep coming up empty-handed?
Not necessarily, because the relevant mass range of the axion particle we're talking about can be different. Also, the energy density in the axion field can actually be quite small and still produce this birefringence. So not necessarily. There is a complex interplay between different constraints from various sorts of probes of axions, including axion dark matter, and these birefringence scenarios. But there are still parts of the model space which could do this. Yeah.
Okay, let's move on to, because there's so many different aspects we can measure from these observations.
Sure.
Let's move on to lensing power spectra, which I'm guessing is gravitational lensing effects. This is presumably stuff in between the CMB and us, the observer. So is that measuring essentially large scale structure in some way? What are we getting from that?
That's right. Yeah. So one of the natural predictions that we should expect in the cosmic microwave background is that the photons' paths get deflected slightly just from the gravity of the intervening large-scale structures. Einstein's theory of gravity, general relativity, predicts that photons get lensed or deflected by the gravity of matter. This was famously confirmed in the Eddington expedition in 1919. And now we're doing this on the grandest scale using the whole universe. So what happens in the cosmic microwave background is that the patterns in the CMB get slightly warped by this process of lensing in a way that we know how to calculate. And so what you can do is use the statistical correlations induced by these warps to effectively measure the lens field that lies between us and the cosmic microwave background, which is the projected matter density or of the large scale structure in our universe. So it gives us a new tool in CMB to actually learn about the stuff between us and the surface of last scattering and use the statistics, for example, the power spectrum of this lensing field itself as an additional cosmological probe.
Presumably we've measured this. This seems much more tractable. What have we got from that?
Yeah, the state-of-the-art measurements come from the Atacama Cosmology Telescope, ACT, which I work on, the Planck Satellite, and the South Pole Telescope, SPT. The combined significance of all these measurements now is at the something like 50-ish sigma level, maybe 60 sigma. So it's very robustly detected, very high signal to noise. And what this lets us measure is the amplitude of density fluctuations in the universe at later times, so closer to the modern universe. We talked earlier about how when you look in one direction in the sky, you see a galaxy here, a galaxy over here, a galaxy over here. What the lensing lets us do is to do the same type of exercise, but for dark matter, because the lensing is sensitive to everything in terms of gravity, including the dark matter. So when you measure the power spectrum of the lensing field, you're actually measuring the dark matter power spectrum. And we can make maps of this lensing field, and you can just look at the distribution of the dark matter in our entire observable universe.
So this reminds me a bit of baryonic acoustic oscillations, which are also probing structure on a large set of scales. And there was, of course, a huge amount of fuss and excitement about DESI, this experiment, which claimed to have obviously it measured the BAO, the baryonic acoustic oscillations, across a large scale, many different redshifts, and by measuring these ring patterns on the sky, these oscillations, there was a claim that this implies that dark energy is changing. So is there a connection between the lensing spectrum and BAO?
So there's a lot to unpack here.
Yeah. We can do it. This is what we're here for.
Good. Yeah. Okay. So it is true that the lensing field lets us trace out the distribution of matter in the universe. And then when we measure the positions of galaxies, that also lets us trace out the distribution of matter in the universe. They're both probes of large scale structure, but they're very different in some ways. So the key fact with the galaxies is that...
which is BAO. The baryonic acoustic oscillations are tracing the galaxies. Yeah.
Yeah, we're using the galaxies as probes of the BAO, exactly. So the key fact about galaxies that's different is that we can measure a spectrum for each galaxy, which then lets us measure its three-dimensional position in the universe, because the redshift that we measure in the spectrum tells us where it's located. Whereas with the lensing, we really just see what we would call a projected two-dimensional map, but we can get some moderate redshift information, but not so much. Whereas with the galaxies, spectroscopic surveys of galaxies, we can measure the three-dimensional positions. And it's these three-dimensional positions that are really important to measure the BAO, because the BAO is this very localized feature in the distribution of matter. It's very subtle, and so you really need three-dimensional surveys to pick it out. So this provocative evidence of potentially evolving dark energy really comes from these measurements of the three-dimensional positions of galaxies, and using the baryonic acoustic oscillation feature as what we would call a standard ruler to probe how the universe has expanded over the past several billion years.
So these are the same, essentially, these quantum fluctuations in the early universe. As the universe expands, these inflations stretch out, and that causes these structures at the BAO.
Yeah, in fact, we could simplify this even further and just say, actually, what we see in these BAO patterns are the same patterns that we see in the cosmic microwave background. It's the same acoustic, what we call acoustic oscillations, hence the name BAO.
Yeah.
They're just much more subtle than they are in the CMB, because the total matter density field is dominated by the dark matter, and the dark matter doesn't interact with radiation, so it doesn't have acoustic oscillations in it. So in the CMB, of course, we're seeing the radiation directly, and the acoustic oscillations are very significant features. We see these big wiggles, whereas in the distribution of matter in the universe, we're just seeing a little wiggle on top of the smooth dark matter distribution. And that was why it was much harder to measure these BAOs, and that wasn't achieved till about 20 years ago.
So it's a difficult measurement, but it sounds like it is more powerful because unlike the lensing, which is you kind of have like an integrated redshift almost, like you don't really know where it's coming from.
Yeah.
Here you've pinned everything down.
That's
so
right.
And we talked earlier about like how dust is a huge problem for polarization measurements. Presumably you have less confounders in this case. At least I would naively expect. So I get a sense the community has a bit of skepticism about this claim. Where is this skepticism emerging from?
Yeah, let me just quickly walk through basically how this then works. So we can predict what this baryon acoustic oscillation length scale should be based on what we see in the CMB.
Right, just run the clock forward.
Because it's the same feature,
Yeah.
right? And so because I know that, I then have a ruler. And if you hand me a ruler and you say it's 1 meter long, and then you take the ruler and stand some distance away from me, I can tell you how far away you walked by just seeing how big the ruler appears to be. That's the idea of a standard ruler. There's some trigonometry involved, but that's pretty much it. And so what these galaxy surveys are trying to do is to effectively do that experiment on a cosmic scale. So they have a ruler and they're looking at it at a bunch of different redshifts or distances away from us and measuring the distance redshift relation. What we call the Hubble diagram goes back to Hubble, who used different techniques, but same idea. And what is very interesting is that the expansion history of the universe you infer from the latest data from DESI, the dark energy spectroscopic instrument, is that it appears that the expansion history is a little bit different than what the standard model of cosmology predicts. And over the redshifts that they're looking at, the dominant component of the universe is the dark energy. So this implies, after you do some data analysis, fit some models, that potentially the dark energy is not a cosmological constant, but in fact is evolving with time.
Yeah, so the universe became dark energy dominated about midway through its current lifetime. Is that roughly right?
A little more recent than that, actually.
Okay.
It was just a few billion years ago.
So
Yeah.
and that's what the BO data is primarily sensitive to.
At the moment, they go the whole way out, actually, even beyond that into the matter-dominated era several billion years ago. And the hope is with future surveys to get even further out.
Right.
But you need a lot of galaxies to make these measurements, and you have to measure redshifts of every individual one to give you a scale. DESI has already measured something like 10 million spectroscopic redshifts. That's the order of magnitude. Forget the exact number. And their goal with the full survey is to measure tens of millions of redshifts, which is more than every individual redshift survey ever done combined.
One thing that seems difficult with this measurement, naively, but maybe you correct me, is if you're looking in the local universe, or like the recent history of the universe, let's say, and you're saying that the redshift of these galaxies allows me to pinpoint the distance essentially to these objects. And then I can use that to say, okay, here's a bunch of objects at the same distance, that forms a structure. Maybe it's fine to use Hubble's law when you're really, really far away. But it seems like the closer and closer you get to us, you start to have the impact of local dynamics, local motions, peculiar motions that maybe get harder to sweep under the rug that you can when you're really far out. So
Right.
is that, as we get closer, is that something you have to compensate for?
Yeah, so what you're describing is what we call peculiar velocities in cosmological parlance. So the peculiar velocities are just the velocities induced by the gravity of all the other structures in the universe. It is true that nearby at what we call low redshifts, the peculiar velocities are significant, and you have to take these into account. Just type 1a supernova surveys and some of the H0 stuff, these peculiar velocity corrections are significant.
But how can you correct? How do you know what the true, you only see one radial speed, right? So how do you know what fraction of that is cosmological versus peculiar?
So in the local universe, what's done is to actually try to map out the distribution of the matter and then know what the local peculiar velocity field looks like. On cosmological scales, very large distances, the peculiar velocity term becomes very small. And by leading order, it looks like Hubble's law, although that has to also be handled more accurately when you go to large distances, but we know how to do this. But what's interesting is that the peculiar velocities that we're talking about here, they do leave other signatures in the correlations of the galaxies, even the very distant ones that DESI is measuring. And that actually gives you a different set of information than what's in the BAO. So what we do actually is when we fit the galaxy survey data is that we fit for properties describing both the BAO as well as these peculiar velocity features that are induced in the correlations. And the peculiar velocities tell us about, for example, how much dark matter there is in the universe, how the dark matter is clustered. So it provides a whole different set of information. So that's all in there for sure.
Okay.
But in terms of the BAO, it's pretty robustly separable from the BAO feature. The thing about the BAO feature is that it's on very large distances. So if you want a scale, I told you earlier we had a standard ruler. We could say, how large is the standard ruler? The standard ruler turns out to have a distance, a length of about 150 megaparsecs, which is 450 million light years, roughly.
That's inflating these modulations in the CMB up to the current epoch. That should be that large.
Yeah.
Okay.
So that's in what we would call co-moving units. So normalized to the size of the universe today, the size of this ruler is about 450 million light years.
Wow.
So it's really big.
Yeah.
It's really big.
And do this isn't the first BAO experiment. Obviously there were, I think, was it BOSS or EBOSS before this?
Yeah, the previous most sensitive one was called BOSS, and then its sort of successor was EBOSS, the Baryon Oscillation Spectroscopic Survey. So what was interesting was that the BOSS data did not seem to show hints of this evolving dark energy. Everything looked pretty kosher with like standard, what we call lambda CDM, where the lambda is cosmological constant dark energy.
The standard model.
The standard model of cosmology. And that was what probably most of us were banking on DESI seeing, but just with smaller error bars. We just say, okay, like we've confirmed lambda CDM with even tighter error bars. But returning to our point from before, if you don't look, you won't find anything.
Yeah.
So DESI looked. And what seems interesting is that there is a moderate hint of potentially some evolution in the dark energy properties. This would be our first observational clue about the physics of dark energy since it was discovered 25 to 30 years ago. The reason there's some skepticism is just that I would say first, on the theory side, this would be such a significant revolution in terms of our picture of the universe, as well as fundamental physics, that I think we need really, really convincing evidence, like 5 sigma plus. There's no combination yet that's 5 sigma plus. So that's one reason. Just on the theory side, this is just a huge.
It's a big pill to swallow.
Huge pill to swallow. And then on the data side, I could offer some of my own opinions. So one thing that's a little strange is that the place where the deviation seems most strong is a place where the BOSS survey also had a lot of data, and the data points there between BOSS and DESI seem to be a little discrepant. It's 2.5 sigma roughly, so that's not like, it's a huge red flag, but I call it like an orange flag, and it's not clear why they look different. It could have been a problem with BOSS. Nobody really knows, but this remains unexplained. So for me, that's kind of a grain of salt. The other thing that's a little tricky here is that no individual probe on its own sees the evidence for evolving dark energy. I would say the cleanest combination is just do the combination of CMB data with the BAO data, and that combination, which I think is very robust, theoretically well understood, observationally clean, there you have evidence at maybe the 3 sigma level. So that's tantalizing, but definitely not like, let's go rewrite the textbooks just yet. It's only when you combine with type 1a supernova data, which probes the universe at even lower redshifts than you can do with the BAO, that then the evidence in some combinations goes up to 4 sigma. Even in those combinations, it never exceeds 5. So at the moment, it's sort of just this like, well, maybe we're seeing the first hints of a totally new aspect of the universe, but it's such a significant thing that we would want to see it at very high statistical significance before we would fully rewrite the textbook.
Okay. So this leads nice into my next question about the landscape of current cosmological experiments. DESI is obviously an active experiment. Mm-hmm. You've already mentioned ACT, which is now finished, but the Simons Observatory, which is coming online.
Yeah.
We talked about past experiments, like Planck is the most recent space-based CMB experiment. Yeah, let's go through like what is the landscape of what's currently out there, what are each of their primary goals? And for instance, how will we resolve some of these? We'll talk about some of the tensions shortly, but like things like the DESI result, is there going to be a successor to that should get us to like 10 sigma or whatever if it was eventually completed?
Yeah, this is a great question. So I'll try to do a quick survey, but there's enough stuff happening in cosmology right now that I'll probably forget something, and so my apologies to
There's a
those
lot
people.
going on in cosmology.
There's a lot going on. We're in a golden age, and I think the next 10 years for sure will continue to be a golden age. Just last week the Rubin telescope turned on. Okay, so let me start with the Cosmology background, since that's my own passion, although I do some stuff with galaxy surveys too. So in the CMB, Planck was our last satellite experiment. There are proposals for future satellite experiments. The most developed one is called Lightbird, which is a Japanese mission that could fly in maybe 7 or 8 years if it goes forward. But for the moment, there's no CMB satellites operating in space. From the ground, we've made great progress both in Chile with the Atacama Cosmology Telescope, ACT. ACT has now finished. We just put out a huge suite of new papers this spring that I spent 3 years of my life working very hard on.
Which all came out the same day as the DESI results.
One day before the DESI results. Yeah. And we really probed the CMB to unprecedented depth, precision, especially the polarization of the CMB. And one of the stories of the ACT results was that the CMB seems remarkably consistent with the standard model of cosmology. If there's something funky happening in the universe, at the moment, the only hints seem to be in the late universe with DESI.
That sounds very much like how the LHC didn't find any new physics. A lot of people were hoping for it. You pushed it, you didn't see anything, and similarly, ACT pushed really hard, and it just keeps holding up.
So far, yeah. I would say we'll come to the tensions that you mentioned in a minute.
Yeah.
Some of those tensions really do suggest that if there's new physics to solve them, that it should be around the time of recombination. Okay. So if you'd asked me before we did the analysis, I might have thought like there's a good chance of seeing something.
Yeah.
But we did a blinded analysis. We opened the box and we didn't see anything. As you say, it's very similar to particle physics. You run this experiment and you hope to see a resonance where there's a new particle, you don't see it. But it rules out large swaths of the beyond standard model theory space. So in the Atacama, the next big experiment is called the Simons Observatory, which has now started taking data.
Is that the same site as ACT?
It is. It's right there. Yeah. And then at that site, there's also a project called CLASS, which I should mention, which is pursuing slightly different way of measuring large-scale properties of the CMB. Then at the South Pole, there's the South Pole Telescope, which just last week released a set of new results, broadly confirming what we found with ACT.
Is it the same precision as ACT, or better, or worse?
It's not quite as good as ACT in terms of the parameter error bars. It's a little complementary, though, because SPT observes a smaller patch of sky. One property of the South Pole is that the sky doesn't rotate when you're down there. So they can stare at one patch really, really deeply. So they measure a smaller patch of sky than we do, but with really low noise levels. So it's a very high fidelity, high resolution, very sharp image of that patch. And so the data sets are, in fact, somewhat complementary and let us check different aspects of the model. Also at the South Pole, there's the BICEP project, which continues to observe. We talked about that a little bit earlier. They're really targeting these primordial gravitational waves. So that's the landscape at the moment on the CMB front.
Can I ask, what is the difference between these ground-based CMB experiments and the space-based? Why not just always do space? What's the advantage of being on the ground?
If we had infinite money, I think we would just always go to space. Space is great because you don't have to contend with the atmosphere. The atmosphere inhibits us in several ways. For example, it limits the set of wavelengths of light that we can look at because it's opaque at some wavelengths. The water vapor also adds noise to our measurements.
Which is why the South Pole is great, because there's no water vapor.
Yeah, it's so cold that
and Chile is very dry.
Yeah, the Atacama Desert is one of the driest places on Earth. So that's a challenge for us. And I should also say the atmosphere, one of the things that makes it hard for us to do is to measure the largest angular scales in the sky for somewhat technical reasons, but you can just keep in mind, if you want to measure scales that are of order the size of the moon or even larger than that, it's easiest to do that if you're in space and not on the ground. The atmosphere causes problems on those large scales. The challenge in space, one, it's just expensive. And then two, you can't upgrade your experiment with new technologies as they come out. So the cool thing about the ground is that as we get more sensitive detectors, you can just go down to the experiment and put them in. That's not what I do, but I have colleagues who are world-class instrumentation developers, and they have been making huge strides improving the sensitivities of the detectors.
Yeah, plus space-based, they always have to have this like space-ready technology level, right? So the stuff we actually launch is always like 10 years out of date.
That's right.
At the moment of launch, let alone when it's get the survey data back.
That's right. So the Planck detectors, for example, were about 10 years old when they were launched. Of course, space is really stable environment, and the sensitivity per detector is better than on the ground. But the technologies are old. The other thing in space is that you can't launch a really big telescopes. If you want to have high angular resolution, you need to have a big dish for basically doing like radio type measurements. Imagine a big radio dish. The ACT project has a 6 meter dish. SBT has a 10 meter dish. So these are really large objects. You can't launch something like that into space. So there's some complementarities.
Okay.
But space has a lot of advantages if we could get there for doing it.
So to come back to the landscape then, I think the only one we missed off was the BAO, or maybe we missed off others, but what's the future?
So then on the galaxy surveys, so the two main ways at the moment of doing cosmology are mostly CMB projects or surveys, and then galaxy surveys. So the leading spectroscopic galaxy survey is DESI that we've talked about earlier, dark energy spectroscopic instrument. There are a few other players in the game though. So the European Space Agency launched a satellite called Euclid a couple of years ago. Euclid is continuing to observe. I think we'll see first cosmology results next year based on what my colleagues have told me.
Okay.
So Euclid is doing a combination of both spectroscopic measurements of galaxies like DESI, but then also more of these like weak lensing measurements with photometric measurements of galaxies.
So if the DESI result was real, Euclid should easily see it?
I can't make a promise. Let me not make a promise on the record about that, but it would be one of the contenders to help confirm what's going on, for sure. Yeah.
Very diplomatically put.
It's a complicated business. Yeah. And I'm not part of Euclid, so I don't know what the internal data properties look like. The next big thing that came online just last week is the Rubin telescope in Chile. So they're going to do the Legacy Survey of Space and Time, LSST, which will be a fantastic weak lensing measurement. So they won't be doing spectroscopic measurements of galaxies, but they'll have photometric measurements of billions of galaxies. Is going to be just a massive catalog. So that will give us a lot of leverage also. There's another project NASA launched called Spherex, which people might have heard of. Spherex is now operating. Its main science goal is something slightly different called Primordial non-Gaussianity, which is a probe of inflation that we haven't talked about. I'm really interested to see what they find on that front, but their measurements could also be very useful for some of these dark energy related things that we're talking about.
Yeah.
So there's also a bunch of galaxy survey projects, and the last one I'll mention is the Roman Space Telescope that NASA is planning to launch next year. Fingers crossed, knock on wood. Roman's going to be a sensational measurement of both the spectroscopic galaxy positions and also these photometric or weak lensing galaxy measurements. It'll be a smaller patch of sky in terms of the cosmological scales, but still big enough to do really good cosmology with it. So
of all these, which one are you most excited about? Probably Simons, I think you're going to say, because you're part of it. But
of everything that I just talked about, I'm definitely most excited about the Simons Observatory. We have been making huge strides, and some of our internal, let's say, assessments of the sensitivities actually look even better than we were hoping. So, it's gonna be awesome. It's gonna be really, really good.
And what's the primary science goal of Simons?
I would say it's twofold. So unlike ACT, Simons is a suite of telescopes. So we have one large telescope, which is effectively continuing on the science case of ACT, measuring the small scale properties of the CMB at really, really high fidelity. One of the things that we're looking for there are potentially new light particles that could have existed in the early universe that are very well motivated from a theory perspective, in which the CMB is by far the best way to look for them. So SO is going to measure the small scale CMB at really amazing fidelity. That will also let us measure the gravitational lensing of the CMB extremely well. A huge amount of cool stuff with that. And then we have the second set of telescopes in SO called the small aperture telescopes. And these are sort of bicep style telescopes that are looking for the primordial gravitational waves. So that's the primary science goal of those. So it's a twofold experiment.
Okay. So with that landscape out the way, I think we have to talk about the tensions, because along with the DESI result, which got a huge amount of press, the thing I think anyone following cosmology has been hearing about is the Hubble tension has been in the news a lot.
Yes.
We had Adam Rees on here maybe a year ago now, and he obviously is one of the major proponents leading this SHOES experiment that's been detecting or searching for using supernova data to measure the expansion rate of the universe, the Hubble constant, and essentially finding that the measurement you get from supernova data seems in strong conflict. That's sort of the modern universe, you might say, whereas if you take the CMB data that you're looking at and you extrapolate what the current H0 Hubble constant should be, you get, what is it, 67, 68? We don't need to worry about the units too much. Whereas Adam's getting something more like 72, I think.
73. Even.
73. Yeah. So those numbers sound similar, but the error bars are so small that formally this is above 5 sigma, I think, at this point, right? Tension. So this is the famous Hubble tension. So that's my outsider perspective of what's going on. What are the details I'm missing on this, and how much of this concerns you? Or do you think this will be just resolved by people improving their telescope measurements and it will all go away? Where to begin?
Where do we start? So this is a huge issue in the field at present. It has been for pretty much a decade or so now. So if we zoom out a little bit, we have really two main ways of measuring the current expansion rate of the universe, or inferring it, let's say. So one is a direct approach, where you go out and measure the distances to nearby objects in the universe, nearby galaxies, and measure their recession velocity or redshift. And you make a plot of the distance versus redshift. This is the so-called Hubble diagram. And the slope of that plot tells you the current expansion rate of the universe. Hubble himself did this 100 years ago. And that's the approach that folks like Adam are using, but with much more sophisticated measurements and analysis techniques.
And also like Wendy Friedman's group.
That's right. So the other big player in the local distance ladder measurements is the Wendy Friedman group, the Carnegie Chicago Hubble Program, CCHP. Yeah. This approach is nice because it really lets you measure or infer the current expansion rate directly. But it's a challenging measurement because there's a lot of complicated astronomy involved. So measuring the distances to things in astronomy is, as you well know, a very challenging task that's been, a thorn in the side of astronomers for the past 100 years. So there's a variety of methods that are used, but the most precise one relies on these Cepheid variable stars that are used as calibrators in galaxies that also have type 1a supernovas that go off.
These are pulsating stars, which have a very strict relationship between their intrinsic brightness and the pulsation period, and people in principle are using that calibration to back out their distance.
That's right. There's a bunch of details involving things like metallicity and dust corrections and all sorts of complex astrophysics there. Yeah. But that's the basic story. And the most precise measurement comes in at around 73 plus or minus 1 in the units that we use. Okay, so then the other main way of doing this is to go out and measure the universe on very large scales in the CMB, for example, or with galaxy surveys, and then fit a model of the universe to those data. And then as a consequence of that fit, you predict what the current expansion rate should be. So it's an indirect measurement of the current expansion rate. And our current standard model is what's called ΛCDM. It's come up a couple times already, but it's a very simple model at some level. It just contains a few ingredients. So you have the normal matter that we know and love, what we call baryonic matter in cosmology. There's the dark matter. There's the dark energy, which in ΛCDM is just a cosmological constant. And then you have this is actually not taken to be a free parameter of the model, but we have the radiation, the photons. Kobe measured it so well that we actually usually don't allow that to be a free parameter, but it is still a free parameter at some level. And then there are the properties of the perturbations, so their amplitude and their scale dependence. And that's it. It's a very simple model, and it fits effectively everything we've measured over the past 50 years in modern cosmology exquisitely well. And as a consequence of the fit, you predict the current expansion rate and you get about 67 or 68 kilometers per second per megaparsec. And that mismatch now between the indirect approach and the direct measurements is at the 5 sigma level if you focus on the SHOES measurement. So one thing that's been, I would say, an area of active inquiry is to try to pin down the local measurements as precisely as possible and use as many alternative techniques to confirm the value as possible. So Wendy's group, the CCHP group, they've been pursuing A few routes, but their most studied one involves a different type of star, a red giant star. They use this tip of the red giant branch.
Yeah, and we had Wendy on way back as well, talking about this on the podcast. So I recommend people check that out. But yeah, there's a lot of nuance to this, but this is a completely independent way to using the pulsating stars.
That's right. And her group finds a somewhat lower value than what Adam's group finds. It does have a larger error bar, so a larger uncertainty. So it could be consistent both with the shoes measurement and with the indirect measurements. I will say on the indirect front, so the CMB is the most precise way to do this, but you can actually do a similar type of exercise with the galaxy survey data as well, where you mostly ignore the CMB data and you find the same answer. So
As the
CMB. Oh,
okay.
So we have multiple ways of doing the indirect measurement that agree with each other. So that really tells you that there's not a systematic error, for example, in the CMB that is causing this. And we now also have measurements from Planck, from ACT, that I worked hard on, SPT, and those all agree with each other as well.
Yeah, so everyone's agreeing on the CMB, and it's such a clean, neat theory. It just, I think, intuitionally, it feels like if you're going to put a bet on a number, you'd probably bet on that. The only weakness of it maybe is that you're kind of predicting 13.8 billion years into the future, whereas the direct method is direct. It's actually measuring what it is, but that's just a very complicated measurement to actually make.
That's right. So the wrinkle here is that the indirect measurements are indirect. So we have to assume a model of the universe when we do that. And so the reason everyone has gotten so excited about this is that if you really believe everything that I've just told you, then it would suggest that the natural way to fix the problem is to introduce some new physics beyond the standard model of cosmology that would change the indirect inference. So you have to come up with a new model that has some new physics in it that still fits the CMB, which is a hard thing to do. We have tons of data points with tiny error bars that would fit the data, but predict an H0 value that is about 10% higher than what LCDM predicts. And I and many of my colleagues have worked on this problem for about a decade, and we have not found something that seems to work. We've explored huge ranges of new physics, and haven't managed to find something that really seems to convincingly work. Returning back to the new ACT results from March, so the most well-motivated types of new physics that you would introduce to fix this problem, in fact, are new physics that would affect the CMB. So you might think, well, if I want to change the expansion rate of the universe today, I should mess with stuff in the late universe, like the dark energy, for example. It turns out that that is a very hard thing to do because of the BAO surveys and other, let's say, modern universe measurements, late time universe measurements that exclude those kinds of possibilities. And so the natural place you look to fix this problem is actually to go to the early universe. And that's been appreciated now for 7 or 8 years.
And also, don't you run into problems like violating like the null energy condition if you start messing with things at the late end?
Well, potentially, but this DESI result would also could also violate that. Right. Separate topic. So many of us, myself included, really thought, and maybe still think, that the best place to introduce some new physics to fix the Hubble constant problem would be to do it in the early universe, affecting recombination or the times just before recombination. And there have been a few candidate models or ideas to do this, things like primordial magnetic fields or other things that change the recombination physics, this early dark energy model that introduces some new type of field that affects the expansion rate before recombination, variations of the fundamental constants of nature at that epoch. There's only a few things that have been at all viable. So we looked at all these with the ACT data in March, and we didn't see any of them. I tried to be as thorough as I possibly could. Yeah. And my students can tell you that, they were like, do we really have to look at another one?
So obviously, if you don't see anything, you can get an upper limit. Yeah. Do those upper limits, are they sufficiently tight that you can say this definitely is not a possible cause of the Hubble tension, if you believe these numbers?
We put, I would say, pretty significant pressure on almost all the popular candidates. Yeah. In all these sorts of games, like, you can always fine tune some of the parameters more and more to like still fit in the allowed parameter space. But if one of these things was really going on, you should expect to see that ΛCDM, the standard model, would fail to fit the CMB data as you measured the CMB at higher precision. And we very much do not see that. ΛCDM really seems to fit the data exceptionally well. And none of these other models improved the fit by any significant amount, despite having lots of new free parameters. So after, in the past 2 months, I would say in the aftermath of what we measured in the CMB, I'm very much in a back to the drawing board phase. I don't know. Maybe we've just missed some loophole in the theory. Maybe we need to be much more clever. But at the moment, it's not clear to me what's going on. I do hope that on the local measurement front, that the precision will continue to improve. JWST data is still coming in. I think that's helping a lot. There's other ways of doing the local measurements, for example, with strong gravitational lensing, or even with gravitational wave observations from LIGO. And I hope in the coming years that those will allow us to also further pin down the local measurement with many independent techniques and say, yeah, it really is, X, Y, Z, and it really does disagree with what you get from the cosmological measurements. If that's pinned down, we will have to figure out the theory that solves this. And it's one of the big open questions in the field.
It sounds like at the moment there's kind of a lot of finger pointing, not in a bad way, but like there's the CMB camp, which are like, we've checked everything and we're really sure this is right. And then, you've got Adam's group and others saying, we've checked metallicity, we've checked this, we've checked all these effects, we have these multiple ways of measuring this stuff, and we just keep getting the same. So it feels like there's really like a loggerhead of these two independent groups of observational cosmologists who just cannot figure out what the problem is, right?
Well, in some sense, but I would say that in the cosmology world, certainly the one that I live in, there's lots of openness to the new theoretical ideas theoretical models that we could use to fit our data that could reconcile the problem. So we've taken this very, very seriously. The thing that we agree upon in the CMB, for example, is our measurements. Like the data points themselves, you can look at the maps of Planck, ACT, SPT, they match exceptionally well. So the data itself is secure, but the model that we use to fit them, of course, that's up to us. ΛCDM really does fit the data exceptionally well, but we've been very open-minded about trying to fit other models. The paper that I co-led back in March is 90 pages long. We looked at 30 plus new physics models, including, I think, all of the most well-motivated ones. And I would have thought maybe if one of those was really responsible for explaining this tension, some new type of particle, some new type of interaction, that we would see a hint of that popping up.
Yeah.
I was surprised that we didn't see that at some level. But I'm an empirical person at the end of the day. And if that's what the data is telling us, that's what it's telling us.
Okay, so the Hubble tension is just one of these tensions. There's a few others, but I think the most, it's not as important, it's not as high profile, but there's certainly garnered some attention, is the sigma 8 S8 tension. More difficult maybe to explain exactly what this one is compared to Hubble, but can you give us a rundown of what this is and how significant is that tension? And is it at all related to Hubble?
Sure. Yeah. Well, I'll start first with the last point, which is that broadly speaking, we don't think these are related.
Okay.
Yeah. They seem pretty distinct. So the sigma 8 tension or S8 tension, if I wanted to boil it down in a simple statement, is really just a statement about how clumpy the universe is. So we talked earlier about the inhomogeneities in the distribution of matter in the universe. We see one galaxy over here, then a bunch of empty space, then another galaxy over here. So if you think on a large scale, you can boil that down to a statement about how clustered is the matter in the universe? How lumpy is it? Is it mostly clumped up into really dense blobs, or is it more homogenously, smoothly distributed? And
does this come back to the 10 to the minus 5, 1 part in 100,000 from the CMB?
Yeah,
it kind of follows from that.
Exactly. Yeah. The formal definition of this S8 quantity is that it's defined at the modern universe today at redshift 0. And so it's kind of similar to what we were saying with the Hubble problem, in the sense that what we do is we fit a model to, let's say, the cosmic microwave background data, which is in the early universe, and then we use that model to extrapolate forward to what the present day universe should look like. In this case, we're trying to extrapolate what the clumpiness of the matter should look like in the universe. And what we see is that it looks a little bit less clumpy than what the best fit model to the CMB, the best fit ΛCDM model to the CMB would predict.
So there should be more structure now than we see,
according to the CMB prediction.
Okay.
Yeah, exactly.
Interesting.
So that's really what it boils down to. There's a lot of details that we're slightly smoothing over here. So similar to the Hubble situation, if you sort of take it at face value, it would suggest that maybe there is some new physics operating beyond ΛCDM that could cause the matter distribution today to be a little bit more smoothly distributed, a little bit more homogenously distributed than ΛCDM would predict. So we should say, what are the local late time measurements that tell us this? The predominant ones have been from weak lensing surveys. So we go out, we measure the shapes of galaxies in the sky. You have to measure millions of galaxies to do this, but you measure shapes, and the shapes of those galaxies get slightly distorted by the gravitational lensing effect that we talked about earlier, which bends the path of the photons a little bit. So the shapes get sheared just a little bit, and if you measure millions of them, you can statistically back out what the distribution of matter in the universe looks like. So some of the leading surveys doing this are the Dark Energy Survey, DES, the Hypersa PrimeCam survey, HSC, and the KIDS survey, the Kilo Degree survey, KIDS. And on each of these experiments' own merits, they've only seen this at sort of maybe a 2 sigma level, but there've been a few of them now that kind of see it to be a little bit low, which led to this maybe being interesting. There have been some revisions on this front just in the past few weeks, though. So the KIDS survey put out their final results back in March, when ACT and DESI also came out. Big month.
Big month, yeah.
Yeah, and the final KIDS results actually moved their S8 value upwards by a pretty significant amount, something like 2-ish sigma, such that what used to be a tension with the CMB seems to have largely gone away. You might ask, well, what happened? The dominant thing that was improved was their understanding of the redshifts of the galaxies. So these are not spectroscopic surveys like DESI, where you can precisely measure the spectrum of every galaxy. They just make photometric measurements in a few broad filters for each galaxy, and then try to estimate the redshift just from those few colors, basically. And that's a very hard problem. Which was a big problem.
I think James Webb had a big problem with that early on. Right, yeah.
Yeah, for these high redshift galaxies, ultra high redshift galaxy candidates. So they've improved their understanding of these so-called photometric redshifts significantly, and along with a couple of other systematics that led to their S8 value shifting upwards. So the latest hints suggest that perhaps the S8 problem was just a statistical fluctuation, an anomaly, a little bit of systematics, and that is mostly going away. Many of us are definitely still paying close attention, though. The Dark Energy Survey is going to have their final cosmological results, I believe, by the end of this year, maybe even this summer. I just saw some colleagues, and I hear that it's going along. So hopefully by the end of the year. And that's totally independent and should have a very precise error bar. So it'll be interesting to see how it shapes up. The CMB lensing measurements I talked about earlier, those also have some bearing on this issue. CMB lensing probes the universe at a somewhat earlier time or higher redshift than the galaxy weak lensing surveys. But from CMB lensing, we don't see this S8 suppression. We don't see this tension. So at the moment, if you asked me a few years ago, I actually thought this looked like a place where there could be a smoking gun of some new physics. Right now, I think, for me at least, the vibes are shifting a little bit away from that, and it's looking more concordant.
So it is obviously easily possible in that situation this could disappear in the coming years. Similarly, it's possible the 3 sigma tension of the DESI result might not be confirmed and might disappear, might be a redshift problem there as well, possibly. And it, maybe it's a harder stretch because it is so significant, but the Hubble tension, maybe someone realizes there's something wrong with the Cepheids and they all get recalibrated, and Adam would be spinning in his office wherever he is, thinking about that.
This is just a guess.
But it is possible. It is possible that all of these
science is complicated.
Tensions would go away.
Hard work, yeah.
And so we could end up in a situation where lambda CDM prevails, and we have these next generation of experiments, and it just continues that way. It just continues that we just keep nailing it down. And actually, what put me off studying cosmology as a student was exactly that picture. I remember being sort of told at the time in lectures that the future of cosmology is more or less just to measure everything to ever greater, we'll go from 1% precision to 0.5% precision to 0.1. And it just seemed like, oh man, that doesn't sound very interesting just to measure precisions. It doesn't feel like that right now with all these tensions. The tensions have almost revitalized the field and given it such a sense of urgency. So a possible outcome is, though, that it just all kind of goes to standard model forever and ever. Indeed, it could happen with particle physics and many other fields as well. Mm-hmm. But another outcome is that these tensions are real, and we have a complete transformation of modern cosmology. So yeah, maybe we can just put your speculation hat on, and you can also tell me your desires as well, because I'm sure you have a preference as to which one would. And I know that the ACT team, and led by Spergel, I interviewed Spergel on here as well, and he's kind of notoriously very conservative. Like he really demands very high levels, as scientists should, very high levels of evidence before we believe that lambda CDM should be thrown out, because it's just been astonishingly successful. And so we should give that a lot of credence. But do you have a crystal ball? If you were to look into the future, do you hope, do you believe that lambda CDM will survive the coming 10, 20 years?
Well, I can give at least a couple of different answers to this question.
Yeah, this is very speculative. So this is your chance to give opinions. This is not backed by like an evidence at this point. We're just speculating.
Right. I will say, like David, I do have a very high threshold for sort of like believing that I should update my current model of the universe.
Extraordinary claims, extraordinary evidence.
Yeah, especially if it's something that's really exotic. For example, like the evolving dark energy claim from DESI. I will say, I hope that in the next 10 to 20 years, we see a significant hint of something unexpected and that lambda CDM has to be revised. I do think it's possible that might not happen, though. To give a more precise answer, we should also define really what we mean by lambda CDM. So we use lambda is the lambda of the cosmological constant, and the CDM is cold dark matter. But that's just a fraction of what's really in the model, because there's also the baryonic matter that we're made of, there's the radiation, there's also neutrinos, which we don't mention. But cosmology is actually very sensitive to properties of the neutrinos. And one of the expectations of the next several years is that we'll make a detection of the mass of the neutrinos from cosmological data. This has actually been an area that there's been some recent, let's say, activity in with DESI and other surveys.
Yeah, I remember the DESI paper had some limits on this that caused a furore on
right now
X
we
and
have a surprisingly tight upper limit, such that the posterior peak appears to be effectively negative neutrino mass. There's not actually a negative mass in the thing, but that's just the apparent peak of the posterior.
But isn't the lower limit from DESI equal to the upper limit from particle accelerators or something?
It's the other way around.
Okay.
The particle experiments, neutrino oscillation experiments, included by some of our friends here in the physics department, they measure a minimum summed mass, but they don't know what the actual mass is. So they can tell you there's a lower limit of about 60 millielectron volts, but we don't know what the total mass is. Cosmology is very sensitive to this through the way that the neutrinos affect the growth of structure. So I would say the vanilla expectation of many of us in cosmology was that we would continue with lambda CDM, and then we would see the neutrino mass, and it would be our first sort of like natural extension, and it'd be like, oh yeah, we predicted all this, like, we know what we're doing as theorists. But the universe, can give us surprises. So the DESI measurements have been like the biggest curveball of the past few years for sure, and maybe humbling us to say that the universe could do very unexpected things. And so it's important that we keep measuring it. Returning to the point you're mentioning earlier about just confirming things with smaller and smaller error bars, I think it's really important to always remember that in physics and astronomy, huge breakthroughs do happen when we improve measurement precision. Even if we don't know what it was that we were going to measure with the higher precision, just by virtue of having higher precision, that's how big discoveries happen.
Yeah.
And that's been the story of the past 200 years, I think, in progress in physics. And so cosmology, I think, is no stranger to that. If you look back at the 1990s, no one expected that the universe was accelerating, really. Maybe Steve Weinberg was like, oh, there could be a cosmological constant, but not really. But people wanted to measure the distance redshift relation to try to measure the density of matter in the universe very precisely. Adam Rees, who we talked about earlier, is one of the people doing this. But by virtue of going out and trying to measure that more precisely, they found a total surprise, which is that, in fact, the universe wasn't dominated by matter today at all. It's dominated by dark energy, the cosmological constant, and the expansion is accelerating. I think it's entirely possible the universe will throw us some curveballs like that in the coming years. Beyond the neutrinos, some of the things that I'm personally most excited about or hope that we might see are things that probe the properties of inflation. We talked earlier about primordial gravitational waves and whether we could expect to see those. It's a total open question, but it would be, in my opinion, the coolest thing that we could measure. I mean, just seeing the beginning of the universe pretty much directly is, what else could you ask for as a cosmologist? So that's one. The other one is something that I tangentially mentioned just a little bit earlier, which is about primordial non-Gaussianity. This sounds complicated, but that complicated. It's really just about these inflationary perturbations that we talked about earlier from quantum mechanical fluctuations of the inflaton field. So in the simplest models of inflation, these perturbations follow a Gaussian distribution. So they look like a bell curve where you have most of the distributions are close to zero, fluctuations are close to zero, but some of them are out in the tails. But there's a range of models that predict deviations from that Gaussian bell curve. And it turns out that these subtle deviations called primordial non-Gaussianity tell you a huge amount of information about the physics of inflation itself. They're kind of, in some sense, like running the particle collider and telling you what the interactions of the fields were at the beginning of the universe that were causing inflation to happen. The Spherex satellite, one of its main science goals is to try to measure this primordial non-Gaussianity. Our upcoming measurements from the Simons Observatory should also be really fantastic for improving the sensitivity. So from a physics standpoint, for me, at least, that's one of the things where I hope to see a deviation. Technically, this Gaussianity of the perturbations is part of ΛCDM. We don't say that's not in the name. It's not like a Gaussian ΛCDM, but it is there. And if we saw a deviation, some primordial non-Gaussianity, that would just be a revolutionary discovery beyond ΛCDM. It would tell us something new about the dynamics at the beginning of the universe. So for me, that's definitely a place in the next couple of decades where I really hope maybe the universe is kind to us and throws us a little curveball to get excited about.
Well, I really appreciate your time, Colin, and I think you've definitely got folks excited about how active and how much new work there is happening in cosmology right now, and it is far from the story I was told. It feels the opposite of a stagnant field, and I keep finding myself more and more fascinated by what's happening. So I'm keeping a very close ear, and I'm sure the next time there's a huge discovery, I'll be knocking your door, as I often do, asking, and hopefully we can have you back in the future as well with Simons Observatory results down the road.
I would love to come back. Yeah, thank you so much for having me. This has been a lot of fun. Let me just close by also saying thank you to everyone in this country and around the world who generously supports the work that we do.
Yeah.
These projects that I've been talking about are largely funded by taxpayer contributions. We're some tiny fraction of the federal budget in the United States. But all these revolutionary ideas that we're talking about fundamentally are paid for by our fellow citizens. And so I'm just very grateful. And let me just thank everyone who's contributed to let this happen over the past several decades. And I hope we can keep doing it because, as we talked about, there's a lot of cool stuff. There are hints of potentially really exotic fundamental discoveries at hand. And I'm just super excited to see what we find in the next few years.
Here. Yeah, thanks again, Colin. So that was my conversation with Professor Colin Hill. So pleased he could join me on the podcast for this one and give us a real deep explanation of many of these foundational concepts in physical cosmology. As I mentioned in that episode, I do feel a little bit, I don't know if betrayed's the right word, but let down by some of my professors I had as an undergraduate at Cambridge University, because I do remember getting the impression, and maybe it was a miscommunication on behalf of the lecturers, but I certainly got the message that cosmology was entering an era of just sort of nailing down these numbers to ever greater precision. So omega matter, right? We already know it to whatever, a few percent precision. In the next few years, we're going to get down to sub-percent precision. And that's really all there is to do left. And, sometimes we get the same impression in particle physics as well. I think when I was studying particle physics, I think I got the same kind of message that we've discovered all the major particles at this point, and now it's just a case of dialing in those numbers to ever greater precision. And in both cases, certainly in physical cosmology, which I'm a little bit more closer to, it is absolutely wrong. And I guess I feel a little bit betrayed and let down by that, because there is so much fascinating work happening in that. I kind of wish to some degree I could have spent more time researching that topic as well. But I guess through this podcast and through my research, not my research, but as a science communicator, I get to kind of dip my toe into that world, and I get to indulge in that and actually maybe satiate that appetite for physical cosmology a little bit. So I really appreciate people like Colin coming on and explaining all of the wonderful discoveries that are happening. And who knows, maybe one day I'll switch to cosmology, because it is just such a fascinating field. And I hope if you are someone who is interested, maybe we have some young people, some students listening to this who are thinking of getting involved in science, I hope it gives you the impression that this is not a field which is hitting a dead end. This is a field which is, if anything, just exploding. Like, we are seeing revelations, and we are about to really rip at the fabric of our understanding. These standard models are really coming into tension now. Something is going to give, and when it does, it is going to be a whole new breakthrough, right? We're going to have, probably the next Einstein at some point is going to figure out some deeper theory, or maybe be a whole ensemble of people figure out this deeper theory. But there is something clearly there that we are missing. And hey, that is what you want in science. You want to be alive at the time when discoveries are happening. And it feels like that in cosmology right now. So I hope you enjoyed that conversation. We're going to have some more cosmology talks on here, of course, going forward. I know you guys always like a bit of cosmology. I do too. If you want to support this podcast, what we're doing here, trying to have these conversations, my philosophy with this podcast is a scientist talking to another scientist, but I often ask the dumb questions. I hope you realize sometimes I'm asking these dumb questions. I know the answer, but I'm trying to sort of lay the groundwork for you guys to follow along. I'm trying to ask the right questions, but sometimes in a foundational way. That's putting my science communicator hat on to help you guys penetrate these very difficult fields. So if you think this is an important series of conversations that you want to see keep going, then the best way to support us is to head to our website. That is coolworldslab.com, coolworldslab.com/support. Okay, so that's coolworldslab.com/support. Head there, and there's a whole bunch of membership tiers you can hit. You get exclusive access. You can even get access to the Discord, do some live streams together. We can have a one-on-one chat. So you can head over there, choose a membership level that you can afford. It can be anything from price of a coffee per month and upwards. Head over there. Supporting that really helps us out because it means I have to spend less time writing proposals and research grants because all of that money just goes to research. And it means I can spend more time making these conversations, these podcasts, and the other YouTube content we do as well. So please do check that out. And as always, I will see you in the next episode. So please stay thoughtful and stay curious.